So actually, I really would like to welcome you all very much to the ELLIS network. I mean, I have been one of the co-founding actually people when we did this sort of in the early morning, literally at NeurIPS, right before everyone else woke up, because Europeans are on a different time schedule. It was pretty, at the time, it was quite some journey since then, right? We have been putting this together. We had no idea if that's going to work, but now I really have this ELLIS network, right, all across Europe. It's a great opportunity to be part of this, and if I want to single out one thing, it is really the ELLIS PhD and postdoc program. It's really, really exciting to go around, really work with the best people in Europe, and being sort of, immersed in this network. I would highly recommend any young person to really take advantage of this. This is sort of the key thing, in my view, for this ELLIS network. Okay, yeah, great. So thanks very much for having me. What I thought I'm going to talk about today is not about the great things we can do with deep learning, but also actually some of the challenges that we have with this. And I'm going to pick 3 here. Interpretability, robustness, and security. And I'm not going to talk about 300 papers or something. I'm going to talk about a few papers that I think are quite nice in this direction. Something about inherent interpretability of deep networks, and I'm going to motivate why I think this is important. Robustness, I think, is another thing that we don't really have with these networks these days. And then also a bit about security, depending on time, I guess. Right, so the first one is really this inherent interpretability, and that's joint work with Mario Fritz, who also happens to be in the ELLIS unit, and Moritz Bülle, who is a PhD student, a joint PhD student of us. And let me just briefly motivate. So we know these deep networks are very good at sort of giving us good predictions, like for this example here, being able to classify that as a goldfinch, the yellow bird here in this picture. But we also want to understand why the particular network actually chose that particular decision. Right? We want to have explanations, right? Interpretability. And there's multiple reasons, right? I'm not going to go through all of them, but some is, for example, you want to gain trust what the network does. We also want to detect biases, right? If we know what the network is attending to, we can actually detect, right, if there is something going off, right, in the wrong direction in terms of what it actually uses as information, or just simply to understand better, to debug and basically improve on this. So obviously, this is sort of an important area that lots of people have been looking at, and there has been requirements, right? Some of the requirements I want to pick out here. The one is that it's when you have an explanation, it should be faithful to the network. That seems to be totally obvious that if I'm explaining something how the network did it, right, it should be faithful. But it turns out actually that many of this explanation methods that we currently have are not as faithful as you would expect. I'm not going to go into this. There's another paper about this at CVPR this year where you can look this up. But really, the faithfulness is something that's actually not quite as given as one would hope for. And then the other one actually is very important, that actually it's also interpretable by humans. If you look at the explanation, it should be really something that you as a human see that it makes sense to you as human. So let's take one of the examples, right? Sort of one of the classic methods is just, looking at the gradient, right, at the point of your classification, and then you're seeing this pretty noisy image. It turns out this is obviously faithful because it's just a gradient locally around where you are basically having your decision. So that's great, but I would argue it's not very interpretable for us as humans. Right? It's not clear if you look at this noisy picture what exactly the network actually is doing, or actually, actually this is what the network is doing, but it's not interpretable for us. We have to somehow change the network actually to become more interpretable. So there's obviously something that people know about, right? It's a long time, and people have been doing something like guided backpropagation, right? And that actually, if you look at this, it looks far more interpretable. It looks like as now the shape of the bird is actually used here for this classification. But it doesn't basically, so in that sense, it's sort of interpretable. It doesn't, though, actually sort of fulfill some of the simplest sanity checks. And here's the sanity check. Basically, we are randomizing out of this 11-layer network, we randomize 10. And if you look at the same explanation, it still is the same explanation of a completely bogus actual result. So that actually is not faithful, right? It basically just highlights important regions in the image, and it has nothing to do with actually the result of the network. So it's nothing that's faithful. So what we want, obviously, is something that's both faithful and interpretable. And the way we address this is we are doing something we call dynamic linearity, and I'm going to say what that is in our view. That makes it then faithful, the network. And we also want to make it interpretable. We're really having a new network which aims to generate sort of explanations and actually sort of decisions based on something that is human interpretable. And for this, we need the alignment pressure, and I'm going to get to this in a second. So what is this dynamic linearity story? So we have a network. It's a deep network with multiple layers. And each of these network layers actually itself just calculates a linear transformation from the input to the next layer. but that, you know, a linear transformation is not particularly strong, not particularly powerful. What we have to add here is something, is what this dynamic linearity is. Now this linear transformation is dependent on the input. And by that way, basically, each of these linear mappings are actually more powerful, and actually we can achieve literally sort of good performance on ImageNet, for example, essentially on par with existing standard networks. Since each of these layers now is linear, right, dynamic linear, the entire network is linear, and then sort of what you see on the right is literally just, you know, that's what you multiply the image with on the right side. This is the picture you multiply with the image on the left side in a really a dot product manner, and then this generates the logic, really the output of the network. So it's really faithful to the network. And what we're getting for the goldfinch is 49% or so probability, and for the other bird here, the bunting, we get like 47%. And again, these are the two explanations for these two high-scoring outputs. So the nice thing is this is literally what the network is calculating. That's what we're visualizing. So that's good, right? So it really visualizes the right thing. It's faithful. This dynamic linearity gives us the faithfulness. So now the question, why is it actually sort of human interpretable? And you can debate this, right? Because at the end of the day, the humans have to judge this. But to achieve this, we do something what we call alignment pressure. Let me actually show here sort of a very simple equation, right? Just because to make the point, actually, this change is actually pretty minimal at the end of the day. So the classic dot product, the classic linear mapping is just, you know, W times X, right? And you can write this down with a cosine. So that's simple, right? We know all this, right? From standard math, I can write this down here with the sign of cosine, but there's no change yet. So the only difference we make in our transformation to replace a linear transformation, we replace this with what we call a because transformation, where we take the cosine just to the power of b. And in practice, we use b equal 2, so we have just a very little bit more here of cosine. And that actually changes the whole game. And I'll show you in a second why that is. We also have a norm constraint. I can talk about this more on the W in order to make it actually more difficult to find the network any shortcuts. So why does that actually make this small change? Why does it actually make any difference? So think about the two-class problem, right? The red dots versus the gray dots. On the left, on your left, right? So if we see the linear mapping, right, that actually would do this classification, would have this vector to the right. Okay, it's not aligned with the red dots. It's sort of looking orthogonal, obviously, as a linear classifier would do, orthogonal to the decision surface. On the right, on the other side, right, you have this, you know, again, a linear classifier, which actually shows in a different direction now, right? So these explanations, if you use the linear mapping, would be different for the left and the right case, right? If you use this linear mapping. So now if I basically increase this b, that's the only thing I'm doing in this case, right? And you see on the left the b as it grows. What happens is these two minima of this optimization actually coincide, not perfectly, but essentially. And at the very end, you see that vector that actually comes out, this linear mapping, this dynamic linear mapping, now is perfectly aligned with the red dots, with the one class. And it's the same in both cases. That's the whole trick, right? And it actually sounds surprising how little change that is, how much it actually brings. But the point being is you can, because the linear transformation is such a general thing that you have in all these deep networks, you can actually really implant it in all kinds of networks. And we did this in all kinds of convnets, in transformers in the meantime as well. So how does it really look? So in terms of explanation, so here is now these images. These are classified, right, in their respective classes. And now I'm hoping that the projector does this roughly. So here, this is again, right, really what that's the dynamic linear mapping that we're doing from the input to the output to get the logic, right? So to do the classification score. And that, you know, it's pretty detailed, pretty fine-grained. You can actually see what is picked up here. And that's just for contrasting, this is what the other explanation methods do, even for the exact same network. So really, this is not quite good, right? So the GradCam, for example, is a very standard method people do. It's very bloppy, that's sort of the third row here. And the thing is here, the problem is that it only explains the very last layer. It's really not appropriate to use it for the first layers, where you really want to explain everything. Anyways, I think this is sort of, I think sort of we can obviously show qualitative and quantitatively that actually this is quite convincing, but I think this picture already drives the point home a bit. What we can also do is now, because this whole network is dynamic linear, right? So we can actually, you know, pick out individual neurons. They're also dynamic linear. They also have the alignment pressure for every single neuron. So now we can visualize individual neurons. So here we find a neuron that actually fires on some wheels, right? As you can see. So here's some neuron that fires on faces, as you would expect in sort of these data sets. Here we find some neuron which, you know, fires on some dog face with the tongue out. Remember that sort of ImageNet has some 200 out of 1,000 classes or so have dogs, so you have to be really good with dogs. And then you also find something that actually is a neuron that actually picks up on watermarkings in these images, right? And it turns out that actually if you look at ImageNet, it's collected, right, from some sources. They put their sort of watermarks in there. There's sort of some more for some classes than others. This is a perfect spurious correlation you find that actually helps you with classification of ImageNet, but obviously it's nothing you really want to pick up, right? This kind of visualization shows there's something wrong that the ImageNet classifier does here to basically do this kind of classification. Okay, so I want to wrap this first part up by saying sort of here, I argue we really should be working on this inherently interpretable networks, and I'm arguing we really need to have different networks because the current networks are not inherently interpretable. The way we address it is with this dynamic linearity and with this alignment pressure to get faithful and interpretable results. Actually, I haven't shown this, but we actually are competitive on standard benchmarks like ImageNet, and we can actually give this interpretable explanations. Okay, let me move on. The second part, which is about robustness, and I also like to call this sort of the bright and dark side of scene context, as you will see in a second. So, right, again, it's a series of papers, again, together with Mario, actually, and this time the student is Rakshit. And here is sort of the problem I want to talk about. So here on the left, we have an image, right, where we have a street scene, and then on the right, you see sort of the semantic segmentation results. So every single pixel is classified into a particular class, like street and building or people and sidewalk. And this looks all good, right? That's in that case, it's an UberNet, right? It's at the time was a state-of-the-art network. But now if you look carefully right at the bottom image, we have very carefully edited away sort of the cars here on the left side of the road. Right? The cars are not, the parking cars are not in the door there anymore. And then what happens if you look on the right, the sidewalk on the right side of the street is not really, classified correctly anymore. I mean, but think about it, it makes sense, right? If there's parking on the one side of the road, it's more likely that it will be sidewalk on the other side of the road. Perfectly fine as an intuition, as a context information. The network is picking this up. That's great. But actually it's also bad, because as soon as there are no parking cars, for whatever reason, it will not have the sidewalk detection anymore. So at the end, it's a problem that it's actually overconfident using this context. And what we wanted to do in this case, so that's the bright and dark side of context, on the one hand is understandable, it's the right thing to do, but we have to somehow sort of deal with it that actually it also does it when the context is not there, like the parking cars in that case. So here, what we wanted to do is to better understand this problem, right? And we looked at the co-occurrence of objects, right? If there's one object is gone, actually how does it influence the other object detection? And we wanted to quantify this, but then also finding a way of to get over this to a certain extent at least. And we started actually by sort of a weakly annotated method that can remove objects. So here, this was a NERSC paper. I'm not going to go into any further detail, but you get the picture. In the first row, we have sort of images with a particular object, like the first image is a dog. And at the bottom row, we basically have removed the dog, essentially with an automatic fashion without actually really having annotations where the dog is. But that's roughly okay. It's not perfect, as you can see, but actually it does sort of a reasonable job. Once you have this, right, you can go for an image, like on the upper right, you can start removing individual objects, right? On the very far right bottom, we have removed sort of the screen, right? And then we can say, are you still detecting the keyboard and the mouse? Right? In the middle, we have removed the keyboard. Can you still detect now, the screen and the mouse and so forth? And in certain cases, as you would expect, for example, a mouse detection heavily relies that the keyboard is sitting around, right? This basically you can discover by these ways, basically removing objects one by one and actually seeing if actually the score is still reasonable. So we did this, and then whenever we discover these problematic cases, we basically injected more of these sort of not yet covered contexts, right? So in order to basically improve the network, we basically do data augmentation by having more of the relevant cases put in. So this actually, here in these cases, so here the top image again, right, is sort of the image, right, with the cars, and UberNet does it fine. Our method does this well as well. But then if you remove the cars in the, for the bottom left image, right, again, there's a sidewalk, and all of a sudden, in that case, appearing. If we do this data augmentation, we can actually get over this. So this is the example from the motivation example at the beginning, right? Again, on the bottom right, if we do this data augmentation, we're finding the sidewalks even when there are no cars here on the left. And here's actually another case which I find pretty dramatic. So here, the grass detection right at the top right gets replaced by earth detection at the bottom, only because the trees are gone in this image, right? There's the trees at the top right, and only because of this, right, we don't see the grass anymore. And for us as humans, it's not understandable why this should be the case, right? So they're locally, looking at the image, it's clearly grass. That's not earth. And again, if you do the state augmentation, that works quite well. And maybe this is the most interesting example in my view. So here there is sort of the sort of at the top again, right? You see the UberNet actually sees, nicely the road. But if you remove the car, the UberNet actually does not see the road anymore, right? Because the car is missing. I mean, it's kind of funny, right? In order to know where the drivable surface is, you have to detect the car first, right? To basically detect the street. And actually, if you look at this image, this is sort of a reasonably sort of unlikely case to see, right? You have sort of the wet street, it's a snowy region, you have very little data of this type in your data, right, to start from. You're somewhere in the tail, right, of your distribution of the data. Sure, you can go out and you collect more and more data, but then the tail will be just moving elsewhere. So this is a classic case where you were never going to basically get enough data to really cover all the corner cases, all the tail cases. And in here, right, so in order to get over this, you have to be slightly more systematic, right? And here, I guess what we just did, it was just a starting point, right? Trying to understand what kind of co-occurrence statistics are used. And then once you do this, right, in this particular case, we can cover this. But really, you need to basically better understand what these spurious correlations that exist that are really sort of, not helping us in the long run. Okay, so we went one step further with this work, and we tried to really do this in something what we call a semantic manipulation. Because as I said, right, so here we just had been able to do this co-occurrence statistics, but if there's co-occurrence statistics, actually not going to solve us everything. So what we tried is sort of, rather than, we've tried to find cases, and I'm not going to go much in detail obviously here, really cases that are semantically similar, right, to the cases that we can do, but really try to push the network such that it actually starts making errors, right? So it really starts pushing it. So here in the green case is what you have in the training and test data. That's what your IAD classic called, sort of the independent and identically distributed. And then you try to really push it over to the boundaries in order to fool your network. It's sort of in this adversarial setting, you try to really fool it, but it shouldn't be adversarial noisy thing, but it really should be semantically plausible stuff, right? And we can debate if that's the cow, right, or in the middle in the red region, but that's something where the network starts to tip, right? And that's the question, right, then what to do, how this, if this is sensible error or not. So I'm not going to talk much about how we do this. So we're having sort of a weakly annotated thing where we're starting with an input image. You want to basically replace the bird with other birds, and other birds are here defined as a convex hull in some latent space, where we basically synthesize this, and you see the semantically adversarial image in the middle, and that basically is basically generated by sort of failure cases of the detector. Right? We have this trying as in its adversarial losses are, right? We try to fool the detector, and basically he looks for an appearance of the bird here that actually fools it. And here's an example of this, right? So here, we're starting on the left here, there's a bird image, right? Then we replace it with something of our convex hull. And then as we move to the right, we basically fool our classifier that if there's a bird. And at the very end, right, it sees actually this, for us, it's clearly a bird, right? But the classifier sees there's a dog with a frisbee. Right, and it's basically, I mean, but it's adversarially speaking, it's really doing the job, but it's actually, visually at least sort of not, right, for us still sort of sensically that, any network should actually say there's a bird. So what kind of problem cases can we find with this? And I just give you 3 categories, which are sort of the ones that seem to be the most obvious ones. This one is which we call camouflaging, right? You take sort of some picture, here it's a stop sign of a class, right? And then you basically, it merges with the background. You're lacking the contrast that the class classically have. I mean, that it happens to be black here is just, it's a coincidence. If there were another background, it would be another kind of background camouflaging. But it's real, I mean, we as humans, right, are still seeing a stop sign. Clearly, so it's a stop sign that is less sort of a canonical case of a stop sign. So in that sense, it's okay if the network has a lower score, but it should not miss it completely. And here it's completely missing it. Another thing is which maybe it's a bit more expected if you're taking a motorcycle here and then you change the appearance, right? So the form is still about the same, but if you look closely, I'm not sure if how well it shows of the projector, but here there's all kinds of stuff now on these appearance-wise that actually are different. It becomes all of a sudden a backpack, right? Which, again, clearly it's not a backpack. And yet again, we're finding these context things, right, where there's a person in the air. I'm not sure who is sort of, proficient enough to do this kind of jumps. I'm not. But anyway, so there are people who are able to do this, right? You're jumping in the air. Now, if you're in the air, right, all of a sudden, if you change the appearance a bit, it could be an airplane, right? The context here makes perfect sense, right? Except that, the airplanes don't fly as, low on Earth. But anyway, so in principle, you get the point. Right? The context here, again, is something we're finding by this very sort of way of attacking these networks. And by the way, we did this not just for detection, we also did it for semantic segmentation, but in time of interest, I'm not going to show this here. So now here's actually an interesting table, which actually sort of, after we trained this, so we can generate the semantic adversarial examples, and now we can, again, data augment our training sets, and hopefully we are doing better afterwards, right? So that's the idea. In sort of the IID data, where basically the test data has the same distribution as the training data, right, we are gaining a bit, not much. But even in these cases which are constructed to be actually difficult, OOD means sort of out of distribution cases which are really sort of classically not in your training data, right? They're really different kind of distributions, different kind of appearance, whatnot. There we really should shine. And actually we're only getting some few percent here on top. What does that tell us? Actually, that tells us that actually this OOD sampling is extremely difficult, right? So it's just a subset of some of the tail regions. So it's very, very hard actually to even finding good test data, right, to really do this properly. So somehow we can't really rely on our just test protocols we currently have on the test data sets to really see that actually our networks are robust enough for really this long tail parts of our distributions. Okay, so let me again summarize this part here. As I said, right, it's good that the same context is used. But actually, it turns out that they're too heavily dependent on this scene context, right? We have this testing and data augmentation frameworks, and again, I showed you two of those. The one is sort of more direct with co-occurrence, the other one really the semantic adversarial thing. But in my opinion, there is a lot more work to be done. This is really sort of this robustness of our networks is not anywhere close to be solved, right? I'd argue, right? This is really something really traumatic, and I hear this from computer vision perspective, context on co-occurrence and whatnot. But even generally speaking, right, the networks are not really sort of predictable in sort of their outputs. Okay. Yeah, then move on to the last topic that I wanted to briefly talk about, which is sort of a bit of more security setting. And here again, it's two students are involved here, Tribhuvanesh and June. And what's the setting here? So we are having lots of machine learning models, right, that we're using. If you're basically an entrepreneur, right, you might actually, train some particular model and you want to sell it to customers, right, through Google Cloud or Amazon Cloud, doesn't matter, and you want to sell each query, right, to the customers, right? So the customer, right, the user gives you some query and give you some prediction back, and you paying a bit of money, right? Or he pays a bit of money to you, obviously, right, to do this. So now the question is, how much, just by having these results on your images, right, how much actually does the user gets as information out of this prediction outputs? And we did sort of a first experiment where we trained actually many networks, and the question was actually, can we infer sort of inherent sort of properties of the networks, right? Is it the architecture, what kind of activation function, if dropout is used, max pooling is used, you name it. So all kinds of properties that people know are important to make things work. Right? And the hypothesis is, if I look at the prediction outputs of my network, right, at this probability vector, there's a fingerprint essentially about all this information somehow, right? What we did is essentially, right, so the hypothesis, there is this information somehow in these fingerprints, in these, probability vectors, and we basically trained sort of a whole bunch of networks sampling the space of these architectures, right, basically having these images here, then pushing it through these networks, then basically just learning a classifier. Was it using dropout, yes or no? Was it basically using this activation function, one of the four, yes or no, right? So very simple classification tasks. And then if I have a new network coming along, right, looking at the outputs of that network, does it actually sort of, can I actually infer this information? So there's a huge table now here. Don't worry about the numbers. Look at the very last number on the bottom right. So the bottom right number basically says in 80% of the times I can actually estimate correctly so this information about activation function, about dropout, you name it, right? And it's not perfect, clearly so. but really I can constrain my search space as an adversary, right, who wants to basically imitate your own your network performance. I basically have actually some useful information what to try out and what maybe not try out, right? So this is actually, in a sense, this is kind of interesting, right? Problem here with this case is we only worked on MNIST, right? So we had to train, prior to this, we had to train, 5,000 networks. That's not going to scale, right? So nice academic result, let's get over it, right? So let's move on. Okay, so what can we do instead, right? So what's the question, what can we really do to actually do this directly, right? So actually what we're really interested in is not the network architecture, we're really interested in copying the functionality. I want to be as good as that guy who has invested lots of time, right, in this, in his network, right? I want to just copy that functionality. So let's think about how this would work. So I have sort of on the guy who actually has his network trained, right? He has some data set, right? He annotates it, lots of everything involved there. He selects a model, he trains, whatnot, all this stuff he does, right? And then he deploys it as a black box model. I don't know what the model is. I only can look at the output for certain input images. I'm the lazy guy, the adversary, right? I'm also collecting my own images. I'm also, I don't want to annotate. I just use now the black box to annotate my data, right? That's basically what the laziness comes from. I select my own model and train it. So there's a few questions, right? One question is, when I don't know, right, what the distribution of the data is, can I still do this, right? So I'm going to get to this, right? So it's pretty surprising. I can use very different data to copy the functionality. If I don't know the architecture, because here I don't know the architecture that the person uses, right? If it's ResNet, transformer, I don't know. And is it actually efficient? How many queries do I need? Some of you might be reminded here, this is model distillation, right? We can have a model and actually do train it. But the key difference to model distillation is, in a model distillation distribution, you have access to the original distribution of the data, right? So you as an adversary know the distribution. In our case, it's very different. We have no clue about the distribution that people use, right? For training the model, right? I'm just using any arbitrary distribution of data. So just to make the point here, right? So the setting is really something like the following. Think about you're imitating, or you want to imitate a bird classifier, right? Here there's actually a cup class with 200 birds. And I'm using images that have nothing to do with birds, right? I'm taking sort of a train image, dog image, bicycle image, doesn't matter. I just feed that to the classifier, I get the probabilities out. I use these pairs of the probabilities and this, and these images, and I'm training my what we call knockoff net, right? And then I'm applying it to images for birds for the first time, and it does a great job actually, right? Surprisingly well. But I really can train it on completely different images. I mean, we did this, and I get to this to a certain extent, right? So we really use sort of this kind of data sets here, sort of data sets, pretty standard, Caltech, cup, right, indoor. In order to push things, we also use something, the diabetes, like retina images, which are statistics-wise very, very different, right? So, but again, think about you're feeding your model sort of diabetes image, right? And then you want to do bird classification. It sounds actually a bit crazy, but it turns out that this is actually quite possible. And again, too many numbers here. Bottom line of the story is I can roughly, with 80% accuracy, right, of the original performance, I can copy that performance, right? If I have 100%, I get 81, right, % in average. If I have images which are closer, I'm getting better, no surprise. But actually, if the images are even further away, I'm still getting, surprisingly good results in copying the functionality. So now the question is, how fast can I do this? So here, sort of on the x-axis at the bottom, right, you're seeing sort of how much data samples you need. So it takes the case of cups, right? So I need maybe 10,000 samples, right, to copy that functionality. Think about, we are talking about cents, right, per query at most, right? You're talking a few $100, right? That actually it takes to copy that functionality. If I'm a bit smarter, a bit of reinforcement learning to do basically optimize my queries, I can do it even faster, right? So it actually is something that works surprisingly well. Does it actually work in the real world? Well, yes, it does. We actually we stole the functionality from API, which is not to be named, right? Because it is obviously completely illegal. But just to prove the point, right? It is actually possible also in the real world. And is it actually possible to defend? The short answer is actually no. And here, the kind of things we did, right? Sort of the top line is when you really have the full probability vector, right? Sort of the bottom line is we only have sort of the argmax or just the top 1 response, so we basically have very little information, and things are in between, sort of you have top 3 or something information. You really can't defend this. I mean, yes, you're slowing down sort of the ability to copy the functionality, but essentially you can't prevent it, right? And that again is scales across different data sets. Okay, so then let me also wrap up this part. Clearly, these deep models have intellectual property, right? So the model information, the data, the annotation, all these things, right? Deploying them with a black box doesn't prevent you basically that people can steal things. They can estimate the parameters you're using, right? The optimization algorithm, your architecture, you name it, right? And even more so, you can, with a few thousand queries, actually you can steal the functionality directly. And you bet actually this is a concern actually for industry. For anyone who wants to basically prevent this. And it's very hard to defend, right? So there's these very simple things, as I said, right? Just, just giving back the top K or just giving the class back or something. All these things are not going to work really well. They're going to delay things, but actually it's not that great. We actually worked, and that's another iClear paper I didn't talk about here today, where we really tried to poisoning literally the output such that actually the adversary has a harder time to basically copy the functionality. You can do it, it's very expensive, and it's not going to scale either, because again, if the other one knows it, right, he can prevent it, as often in these defense mechanisms. That's why I really didn't talk about this. Yes, and with that, thank you very much for your attention. I'm at the end. Thank you.
Great. Thank you very, very much. There are going to be 2 microphones that will go around. Maybe you go on the left side, and then Matteo, you can go on the other side. Right, yeah, so thank you very much for this interesting talk. Now we have time for questions, comments, suggestions. And if you want to ask a question, just maybe raise your hand, and we'll make sure that a microphone will get to you as quickly as possible. So who wants to kick this off? Michael. Oh, sorry. I try to remember who was first, but maybe let's just start here.
Hey, yeah, thanks for a very interesting talk. I have a question about this functionality stealing. So it seems, I mean, if I understood you correctly, you can basically copy the model with just a few thousands of examples, but doesn't that mean that the original model could have trained up to 80% or whatever the accuracy you got was with just a few thousand examples?
So, I mean, they actually refer back to the classic distillation setting, right? So the classic distillation setting, I still need good ways of training the model in the first place, right? And yes, I mean, actually one thing I didn't say here, we did still ImageNet pre-training, so having some things basically pre-trained, right? So in that sense, we're leveraging this, but everyone can use this. But after that, actually, this, in a way, it's a fine-tuning setting. But again, the crux here, the key difference to the classic thinking about it is actually we can use literally completely unrelated images, right? Which actually, this is still a surprising fact to me. Yes, you can think of this fine-tuning after the fact, right, with few data. But actually, it is really the story that there's these vectors, the probability vectors, plus actually this, training it on completely unrelated images is actually surprising. You can still do, again, retina images, bird images, right? So it's really this kind of, that is still, I find, extremely surprising at the end of the day, right?
Mm-hmm. Okay, thanks. Yeah, I had missed the point that you start with a pre-trained model.
No, I didn't mention it, actually.
That explains it, and then, thanks.
All right, I think there was a question over there, and I think Catherine, you also had a question. Yeah, Paul.
Hey, thank you for your talk. I was wondering, how does that stealing of information from the network structure relate to differential privacy concerns, where we are worried that we're giving away the data that we used originally to train the model?
Yeah, so I haven't really talked about the privacy aspect here at all. You're exactly right. So I mean, in principle, I mean, we know that actually in the network there is, I can actually at least if I have a training sample that I'm hypothesizing is part of this, right? Because for that one it has stronger outputs, I can basically infer that actually it is probably, right? The inference attacks kind of thing. So yeah, so that's another thing. I mean, there's for generative models, right? You can actually start generating the data that it was trained on in the first place. No, absolutely. The privacy part is another aspect that I haven't really talked about here, which I think is absolutely important to think about more carefully. And again, right, I don't think anyone has a really good a good way of addressing this. It's a fabulous topic, to be honest, right, to work on. Yeah, privacy is absolutely essential, yeah.
Right, any further? Yeah.
So I don't have a methodological question, but a target set question. So have you applied some of your methods also to not concrete concepts, such as bird and dog and so on, but to abstract ones? You also find them in internet. So for example, what do you expect from images, or what happens if you want to reproduce the top K images for nightmare, for example?
For nightmare. Oh yeah, I mean, okay.
Whatever,
yes.
glory, mercy, dream.
Right, so I'm not really aware of any data set really that does this in a sense, but in principle, to be honest, right, because there will be something in the images that has some correlation with the concept, these networks will pick it up, right? So I would not expect there's any difference, to be honest, right? For the networks, if it's sort of a object class that we think it's semantic, right, or sensical, right, and then sort of more abstract, I mean, it will be probably harder, right, to do this classification, but I don't really see a principal reason why it shouldn't be basically essentially similar in the results.
Right. I guess in ImageNet you also have the branch of abstraction that connects to WordNet, right? So I guess you would find images for that too.
Right.
But what I just wanted to emphasize is basically you don't expect to see so many concrete objects, like you see the bird, you see the person who jumps. But for a nightmare, what do you expect to see? Like there's more. It's more dependent on colors, or maybe you have a sleeper. You wouldn't really know.
I mean, I guess one of the issues with nightmares is actually, though, nightmares differ between people, right? There's a very typicality thing, right? So I think we can more agree on the bird, whatnot. I mean, still, actually, in computer vision, we really actually say there is a 0-1 decision, right, for birds or not. And actually, it's very known from psychology, this is not the case, right? There is really sort of a grading between, right? A chicken, for example, is not a very typical bird. We don't really use this. We are completely abstracting it away, and it's a bit of a pity. And if we get to something like these abstract concepts, we really have to look at this sort of kind of more grading part, I'd argue, right? But again, I think the story at the end goes still similarly, right? So you say nightmare 1, 2, 3, and whatever the thing is, and the network will pick up something that actually is probably better than we would expect.
Right. Yeah. There's the next question.
Thank you very much for this fantastic talk. I have a question for the second part, the robustness. So, like, I always love these examples. Look here, like, you know, it's a skier, and now, like, it's not the skier anymore, like, it's an airplane. But I always wondered, like, you know, we're totally primed as humans. Like, we see the first picture, right? And then we see the second picture, and we see all the context. There must be studies, right, that look at that. And if you put that out of the context, I think, like, a human might also have a hard time. Are you doing studies? Are, like, you know, people doing studies on that? And how does this influence the network?
Yeah. No, I mean, okay, so I mean, to be totally blunt, I'm not doing this, and I fully agree that sort of this priming experiment would be very interesting to see what actually the networks is basically less typical about. I mean, I tried to allude to this a bit actually when I showed the stop sign. I would argue that actually it's a less typical stop sign. The black point, we still are able to do it, right? But it takes more time, right? Sort of, it's not the priming part, but it's still this human part, right? How much processing time, how much it takes, right? So yes, I agree, right? In principle, it would be very nice to see. Honestly, I think it's not yet time to do this because the networks are so bad at this point, right? So they're so easily fooled. I would argue it's too, you know, we can obviously, I think 80–90% of the cases that the networks fails on, right, of this type, I would argue that humans have, I mean, they might take a bit longer, but they're not really challenged, I'd argue, right? So I mean, I think it's a bit early, to be honest.
Okay, so let's talk in 10 years.
Hopefully 5. Right, 3, of course. Any other questions? I thought I saw a few more hands. Oh, Paul again, yeah, sure. Of course, yeah, go ahead, we have time. So, this is interesting.
So about the classification of images where they were context dependent, for example, whether the cars were there or not. You showed always, I think the kind of maximum probability score, like this is maximum probability, the road and not the sidewalk or something.
Yes.
Do we see this context dependency in the whole softmax probability vector that these networks put out?
Yes, so I mean, yes, you're actually right. We have sort of the winner take all, right? We're just showing the max probability, and actually, yes, there is a distribution shift, but actually, I mean, classically, right, when the network is wrong, it's really wrong with sort of a 0 score. So we really see this. I mean, yes, we have some of these. I mean, you saw some of this where they were mixing. So there, I would expect. I haven't looked at these particular images, but there, I would expect there's a bit of a mix of the softmax. Yes, the max is basically here, you know, going around. But we also have cases where sort of it's completely overwritten, right? Sort of this. The score, right? We have really both, yeah.
Thank you.
Further questions? Otherwise, I also have one. So the examples you showed were either on robustness or on security or interpretability. But of course, ideally, we have networks can do all at the same time. So I'm wondering, is there work already with you, with your group, but also others who try to have networks that can do multiple of these properties? And
So actually, this first work, we haven't really digged into this yet much, but it seems, I mean, one of the things I said, we have this alignment pressure, but also we have this norm constraint, right? Having this norm constraint actually makes things much harder to train. So it's actually more difficult because the network in each of the layers has less capacity essentially, right? But actually in turn actually helps to be more robust upright. So we attack these things, I mean in that case adversarially, we find a bit more robustness. It's not perfect, but at least it's measurable, the importance. So yes, robustness seems to be better on that front, right? Robustness in terms of adversarial robustness, not in the semantic context robustness. So yes, I think there is hope in a way. But I mean, one problem we have right now is that many of these networks, right, need a lot of capacity to really be trainable, right? The problem is, I think, it's this trainability versus, robustness and security trade-off, if you ask me. So we have the trouble right now that we have these networks, also we use batch nodes all the time, right, which actually is not helping for any of this either. So I think we're on a road to really actually have to change the network architectures quite fundamentally. Again, the first one seems to have some glimpse of this, but we obviously weren't able yet to show this. Yes, I fully agree, it should be together, yeah.
Right, so it's not a trivial thing to do. It's really, you say, we have to fundamentally kind of change the way these networks are designed and built.
Yeah, I mean, again, as I said, the first network, actually, the thing that the students spent most time with was basically making it actually converge to something sensical, right? That actually, the ideas were out a long time, right? The because, right? The cosine with the B and the because, this was sort of 6 months before we even had a single line written, right? That base name was there, right? But it's kind of, it actually really make it work. That was tricky. Because again, right, because we need this limitation of the capacities of each layers to really get more robust.
All right. Thanks. Other questions? Otherwise, I have another one that I'm curious about. So, I mean, all of this work is, as it is common in computer vision, on data sets that, of course, become realistically, more and more realistically over time. But I'm wondering, what do you reckon in terms of the challenges that you're attacking now? Will they fundamentally change once you go to, let's say, a real car, and you have a real-time system that kind of tries to do all of these classifications? Will this become harder? Will it become different only? So what are kind of the challenges for moving from data sets to actual systems?
Yeah. So I mean, I don't know if you have followed this development. We have about 18 months, right? We have this very exciting work that trains, jointly on images and text, right? And the start, I mean, this for a clip is an example, a line is an example. And the nice thing about this is actually it's not constrained like 1,000 classes or something. We're talking 400 million images with, uncountable concepts actually in there, right, which are actually even in language. Now, in the language part, we have the similarities, and then we have this, the semantic similarities, and then in the image representation has to mimic this. So why is it interesting? Because now we actually they're really showing that they can transfer much better to all kinds of settings downstream, right? Zero shot becomes, or few shot becomes a totally different game, because all of a sudden you have already seen some images, right, of that type. So that's a direction I think that we really have to explore far more, where we're actually starting from some self-trained model, which might be not perfect, right, but actually is much, much broader in terms of its capacity or its ability to extract information that might be relevant later. So I think the ImageNet pre-training is that, right? I think this kind of pre-training is that's what we have to do. Right. So in that sense, it's the ImageNet thinking, I think we're going to get over this within the next year or two.
Yeah, that's what I was wondering. How long it will still live, because, it has been around for some time, and it seems like for many problems it's a bit
but as I said, since 18 months, there's, every 2 months there is something coming out, which is very exciting in that space, and it's really, and Clip is sort of the first one to check out.
Cool. Thanks. Sure. Okay, last chance. Any other questions? Yeah, sure. But there will be a mic coming. It's on the way.
So thank you for the talk. I have a question about the evaluation of explainability methods. So the one you presented, for example. So an explanation can be quite subjective at times. So how did you evaluate your technique, and use humans, for example? And a follow-up question, how do you see the evaluation of these methods shift to automatic settings, for example?
Yes, so there, for the evaluation, there's really two parts to the story, right? So the one part is exactly as you say, about humans, right? Can humans interpret, right? And there we actually have to do human tests. I would still argue, right, when we look at the qualitative results, things actually are becoming sort of better, right? And with this method that I showed you, actually we wrote an entire paper about how to evaluate these kind of things. And one thing actually we did, and there's another paper co-authored by Morris, but actually another first author, where we actually tried to look also, yet you can systematically evaluate these qualitative things. So we are basically binning things, right, in a way that actually, what kind of stuff it is. I can talk about this offline. The other part of this interpretation evaluation actually is sort of, is it actually attending to the right things, right? And there is this, I haven't really talked about this, there's something called the grid game. You have a 2x2 image where there's 4 different classes in there. And then the only thing you know actually that the information that it gets for the classification should be coming from one of the quadrants, because that's where the image class is. It should not come from the other ones. And actually it should be discriminate. Actually, if you have that information is there, it should be stronger than in the other ones. There will be serious information in the other ones, right? If there's background correlation and whatnot. But there should be the method should be actually at least only or have higher scores in the right quadrant than the other ones. So there are proxies for these kind of things. So that when, I mean, it's still not if it does the right thing. If it in the background, it doesn't maybe pick up the right things in terms of what I really want. But at least I can do certain proxies quantitatively as well. So, but you're absolutely right. So that there, for interpretability, it's a bit difficult to do it right, or actually very difficult, and it's not very agreed upon how exactly to do it. So there are certain things people do. Right, for example, one thing they do is they're taking out the most relevant information from the image by covering it. But and then they say sort of that there should be a drop, right, in sort of the explanation. But at this point, you have changed the input, right? What do you expect, right? So it's kind of, network has not seen this, right? So it's not clear what to expect actually at this point. So it's quite a few of those measures that people use are actually not particularly strong, I'd argue. And that's still something to work on, definitely.
All right, maybe a last question, if there is one. Yeah, up there. And then I think we have to also move on already.
Thank you for the interesting talk. I have a question on the security. So first you talked about like stealing architectures, and then you talked about stealing basically the behavior of a black box model. I was wondering if you, suppose you have a black box model, and then you first steal the architecture, and then try to steal the predictions based on that architecture. Yeah. Do you gain synergies from that? Or for stealing?
Yeah.
Okay.
No, I haven't really talked about this. So one of the things, yes, we obviously could do this, right? But it turns out sort of, I mean, one of the things is obviously, how close does have the architecture to be, right? With which you're training your own model, right? Or compared to the one you're trying to steal. And it turns out if you have a reasonably complex, if you're about the same complexity or larger, you're fine. Right, so basically you don't really need to know much, right? So that's the bottom line of the story here. You just have to have something that's reasonably large, and then, right, and then, that comes then the affordance question, what you can afford, but you can basically start to, using something reasonably large and you're in business. So in that sense, it doesn't seem to be that important at the end from the second work that I talked about. Yeah.
All right, so thank you very much again for this very nice keynote.